In our last video, we explored the concepts of Km and Vmax, where Km is going to be the relationship between the enzyme and its substrate, how efficiently it binds, and the Vmax is the maximum velocity that the enzyme can go. So these are some inherent properties that we looked at. We also talked about visualizing these as a Michaelis-Menten plot, which you can see on the top, and a Lineweaver-Burke or double reciprocal plot, which we have down here. And in the last video, we kind of explored where to find the Km and Vmax values on each of these graphs. So the example that we used before was just for a normal enzyme proceeding without any inhibition, just substrate enzyme in their buffer doing their thing. So now what we're going to do is talk about two different types of inhibitors. The first type that we're going to look at is called a competitive inhibitor. So if you think about it, this name actually makes a lot of sense. So you just have to think about what we're actually competing with. So in this case, we have a competitive inhibitor. It's directly competing for access to the active site with the substrate. So it's kind of like a race. Whichever one gets there first gets to be in the active site. So there's a lot of kind of diffusion involved. How much inhibitor we've added plays a role. How much substrate is there will definitively play a role, just like we'll see. So the idea is that this is kind of random. It's not like we'll only bind the inhibitor, but there is a chance we could bind the inhibitor instead of the substrate. So this is competitive inhibition. So we talked about a couple of values, Km and Vmax, again, that were going to give us information about this. So we're going to learn how the Km and Vmax may or may not change due to the presence of this competitive inhibitor. So again, competitive inhibitor, we are binding to the active site. Okay, so let's check this out. Competitive inhibitor. Here's a Michaelis-Menten plot. Now it's important to understand that you can't just go in and measure the enzyme with its inhibitor and substrate without performing the same analysis in the absence of the inhibitor, because you need to have something to compare it to. So here we have our no inhibitor Michaelis-Menten plot. Okay, we've varied the substrate concentration, and you can see the relative velocity here. Okay, so what we're looking at with these green lines will be increasing levels of inhibitor. So you can see kind of what's going on here. To visualize this with a Michaelis-Menten plot, you really have to think about the asymptote. So where is this line going to end up? Where is it projecting to in space? As you can see, our no inhibitor line, maybe it's somewhere around here. Is that +1 inhibitor going to reach that, or +5 or +10? Okay, and it's a little difficult to see on this graph. And the Km, you can also visualize. If our Vmax is going to end up being somewhere around 100, we would want to look around 50 to find our Km. Read over. Here would be our Km. Km. Whoa, Km way over here now. Okay, and so what this is implying is that it takes more substrate to get the enzyme to go at equivalent speed that it would without the inhibitor. Okay, so again, that makes sense because if there's more substrate, there's a higher chance it will bind the enzyme instead of the inhibitor, kind of like just overwhelm it with excess substrate. Okay, but as you can see, this is a little unwieldy to try and find absolute values. So let's take a look at that Lineweaver-Burke plot. Okay, so some pretty dramatic things going on here. Again, our black line will be no inhibitor, so we always have to compare. Don't even try to turn one of these in without at least 2 lines on it. Okay, so here our inhibitor is not there. This is a normal reaction. And we have our competitive inhibitor. okay, with the red line. So just take a look at this and take this in. We know that the y-intercept is 1 over the Vmax, and that the x, the sort of projected back x-intercept, is negative 1 over the Km. Okay, so we will do some math in a little bit, but you don't actually have to do any hardcore math just to look at this. You can see right away that the y-intercept is pretty much the same for both of these lines, but the x-intercept is different. That tells us that the Vmax must have remained the same while the Km changed. Okay, so for a competitive inhibitor, we should see an increased Km. So again, that makes sense. It takes more substrate to get the enzyme to that point. It's plus 10. What is this, like way over here? Than it does without any inhibitor. Of course, in a reciprocal, that moves our line in this direction. So the Km obviously changed here while the Vmax stayed the same. And that's what you should see for something that's just purely competitive in nature. Okay, so we now understand how to compare lines for competitive inhibitor. Let's take a look at our second scenario. This will be for what's called a non-competitive inhibitor. Okay, this is the only other one we're going to talk about today, but there are actually a few other different types like uncompetitive and mixed inhibition, but let's just stick with the non-competitive for now. So non-competitive inhibition, hopefully how this is named plus the visual should tell you what's going on here. Okay, and so the important thing is that this is not competing with the substrate. The substrate can still bind as much as it wants in the active site. What this does is slow the maximum speed. Okay, so this would be like you have a car, you can put as much gas in it as you want, but the speed has slowed down. So this is a mechanism where the inhibitor binds somewhere else besides the active site. So anywhere else, as long as it's not directly competing with the substrate. Okay, so what we're going to see is what this will do to the Km and the Vmax. All right, so check it out in this example. This is our Michaelis-Menten plot for a non-competitive inhibitor. Okay, and I think this one, you know, it's, again, difficult, I think, to really get good quantitative values from this Michaelis-Menten plot when you're just eyeballing it. But you can kind of see that the asymptote, when you're not in this concentration of 1 for this inhibitor, you're not going to get up to this 100 or wherever this asymptote is. You might reach 50, okay? As we increase this concentration, the asymptote is lower and lower. So it's not really trending upwards, especially here. This looks pretty flat. So we've lowered the Vmax. Okay, and again, I think the Km is a little difficult to see here, but for our no inhibitor situation here, about 50, we estimated our Km would be somewhere right around here, whatever concentration that is. Okay, so if our Vmax is 50 for our first inhibitor concentration, we look about 25, head over here, you can see that it's probably within that same range. Okay, again, a little bit difficult, I didn't put lines here, so maybe it's a little bit shifted. It's difficult to see on this, but we can see big dip in the Vmax, potentially kind of hanging out in the same place for that Km, kind of around in here. Okay, again, this should really illustrate the beauty of the Lineweaver-Burke plot over here because it's so obvious when you look at it in a linear form. Okay, so our control line or no inhibitor present, or maybe more like our baseline, what we need to look at, here's our non-competitive inhibitor. You can immediately see the y-intercept is different, the x-intercept is the same. The slope is different because We've changed the Km, or we've changed our Vmax, but not our Km. So this is pretty obvious to see that our Vmax changes here, but our Km stays the same. So this makes sense too, because the Km is an indicator of the relationship between the substrate and the enzyme and how they bind. If this can still bind the enzyme with the same efficiency, but the reaction is just slowed, that's what we should expect. Okay, so this is something that we should expect. Okay, so we've seen how these values will change, both in a situation with a competitive and a non-competitive inhibitor. So these can be experimentally determined. Hopefully, from looking at the axes, you can see that this is something we can manipulate in lab. The substrate concentration we can control, and the velocity is something that we can and have measured in other situations. So in your next video, you get a chance to see film version of the protocol so that you understand what this will look like when you get to it in lab.